We're going to be solving Cambridge IGCSE Chemistry Paper 6 Alternative to Practical October-November 2025 Paper 63. The first question states that a student uses the apparatus in figure 1.1 to show that water is formed as one of the products when the fuel is burned. So basically here we have an apparatus. The apparatus is completely new to our syllabus. We have not done this, and that's the good thing about the ATP paper, that it tests you things that you have not done before. You're going to be tested for concepts, for things, for things that you're going to be seeing for the first time. So it's very important to be mentally available on the spot to solve this paper. And that's the biggest trick to it. No matter how much you've studied, you can do theory, you can do the MCQs paper, but this paper requires you your mental capabilities. So you got to be in a good mood while doing it. You got to be fresh, you got to be in a good thinking capacity while doing ATP. That's the thing, because everything's going to be new. So you're burning fuel here, and that's producing a gas. That gas is going into this tube, and then we have ice in this bar over here, and then over here we have solid X that's being deposited or whatever, and then to suction pump something is going out. Okay, strange. Now identify the item of apparatus labeled W. W is basically a funnel, an inverted funnel, right? I know you guys have been seeing funnels, and funnels appear to be something like this to you guys, but over here they've inverted it. It might be tricky, but that's a filter funnel. So we write it's a funnel. Let's see other things as well. What is this thing? This small tube, that's called a delivery tube. What is this thing called? That's called an evaporating dish. What is this thing called? This is a beaker. So this is a U-shaped flask. You should know all these names. When the fuel is burned, the steam produced passes into U-tube. Suggest why the U-tube is surrounded by ice. So look, what we're doing is we are taking steam into this tube. So basically we have this surrounded by ice. Now why do we need ice? We need ice to cool things down. Do you guys remember? Why do we use ice? We use ice to cool things down. So we're cooling steam over here. So steam is gonna move in from here, get cooled down, and turn into a liquid. So to cool or condense steam, that's the main reason we're using it. To cool or condense steam. Water causes solid X in the U-tube to change color. So what's going to happen? Steam going to move in, steam going to condense. Solid X is going to be probably an anhydrous salt. Anhydrous salts change color when they're subjected to water. So over here, water is going to make the salt change color. Name solid X and state the color change. Now this can be, I know this can be a brain teaser for you guys. You have not done any of this before, that an apparatus like this, or you might be unaware of this stuff, but that's the thing. That's why I say ATP is not a paper for theory guys. It's gonna be a paper for those who are able to think clearly. Okay, so now this salt is gonna change color. We've only studied 2 salts in syllabus that change color, right? In the IGCSE syllabus. Salt number 1 is our anhydrous, not only hydrous. Hydrous is going to have a different color. So salt can be anhydrous copper 2, this 2 is important, copper 2 sulfate, which changes color from white to blue. And the second salt that we've studied in syllabus that you can add over here, it's basically your anhydrous, same anhydrous, cobalt 2 chloride. Cobalt 2 chloride. And this salt is going to change color from blue to pink. You can write any one of them because both of them change color in addition of water. Okay, the student tries to use the apparatus in figure 1.2 to pass the gases produced through acidified aqueous potassium manganate. There is an error in the apparatus so that the gases will not pass through the acidified potassium manganate. Okay, So now we are producing some gases. Okay, the gases pass from this tiny little tube to here, 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 and here. But they're saying that the gas does not enter the acidified aqueous manganate. The problem is that we want the gas to enter this liquid. But the problem is that this test tube, this delivery tube is not entering into the liquid. This delivery tube is finishing over here. So that's why the gas is not going to enter the acidified potassium manganate, because over here the gas is going to come, then it's going to move out from here. We need the delivery tube to be dipped into the manganate part, right? So this is the source of error. Identify the item of apparatus labeled Y. Y is this thing that's called a test tube. So that is easy stuff. Test tube. That's also called a boiling tube. A test tube is a little thinner than this. This thicker one is called boiling tube. Okay, you should know. A test tube is a little thinner, a boiling tube is a little bigger in size. So test tube, you should erase. It's a boiling tube. On figure 1.1, draw a circle around the error in the apparatus. I told you this thing is the error. Okay, so just don't make a very big circle, just a small circle around this. This is the error. The error in the apparatus is corrected. The student observes that the aqueous acidified potassium manganate changes color from purple to colorless. Okay, suggest why the color change occurs. So over here we have to tell that why the color is changing. I told you one thing. You might think that you should write over here. I tell you what, student who study good and are good in theory, what will they think? They'll think we have to write over here that what do we write? We write that, you know, some kind of oxidation happening, that's why potassium manganate is changing color. Yeah, you are correct, oxidation is happening, but that's your theory. This is not your theory paper, this is your alternative to practical paper. Over here you are not required to use your theory skills, so you don't think about it like some kind of oxidation happening. What do? You go to your chart which has your color changes, this chart, and then you go over here and you see that which gas is giving you the color for manganate. That why, which gas changes the color of the manganate? Sulfur dioxide turns acidified aqueous potassium manganate from purple to colorless. Don't use the theory knowledge. Again, I'm telling you, use the charts that you're given with. So over here we write, suggest why the color changes. Simple. SO2 gas is produced. SO2 gas is produced. A student investigates the temperature change. So when you're reading this, you should highlight all the important stuff that's gonna come. Investigates the temperature change when a 5 cm cube length of a coiled magnesium ribbon reacts with excess dilute acid. The student does 5 experiments, so he's going to vary one thing and do the experiment. Experiment 1. Rinse a burette with distilled water and then with dilute sulfuric acid. Fill the burette with dilute sulfuric acid. Run some of the sulfuric acid out of the burette so that the level of the dilute sulfuric acid is at the 0 centimeter cube mark. Use the burette to add 30 cm cube of dilute sulfuric acid to a boiling tube. Use a thermometer to measure the initial temperature of the acid. Record the initial temperature. Add a coil of magnesium ribbon to the boiling tube. At the same time, start the stopwatch. Continually stir the mixture of the boiling tube using a thermometer. After 1 minute, measure the temperature of the mixture in the boiling tube and record this temperature. Okay. Experiment 2. Refill the burette with dilute sulfuric acid. Rinse some of the dilute sulfuric acid out of the burette so that the level of the dilute sulfuric acid is with a 0 cm cube mark. Use the burette to add 25 cm cube. Okay. So over here, the change we gotta see. And what's the change? I hope you guys understood. We have 30 cm cube here and we have 25 cm cube here. So that's the thing. Okay. we are using 25 cm cube of dilute sulfuric acid to a new boiling tube. Use the thermometer to measure the initial temperature and then record the initial temperature. Add a coil of magnesium to the boiling tube. At the same time, start the stopwatch. So we're keeping the amount of magnesium constant, that's 5, and then we're changing the amount of the acid. Continually stir the contents in the boiling tube using the thermometer. After 1 minute, measure the temperature of the mixture and record the temperature rise. Experiment 3, we're using 20 cm cube. Then experiment 4, we're using 15 cm cube of acid. And experiment 5, we're using 10 cm cube of acid. Instead of 25. Okay. So that's what we're doing, changing the amount of our acid in each successive experiment. Use the thermometer diagrams to complete table 2.1. So over here, we write the initial temperature and we write the temperature after 1 minute and then the temperature increase. So we gotta be careful. So this is exactly at the let's see, this is exactly at the 21.0 mark. This is exactly at 21.5 mark. You got to be careful with your decimals. If you just write 21 and you don't write 0, you're gonna get a 0, right? So you got to write 0 so that you don't get a 0. Okay. Over here it's 21.5. No, it's 20. Yeah, 21.5. Then again it's 21.5. This one right here is 22.0. This one right here is 22.0. This one right here is 46.0. This one right here is 35, 36, 37, 38, 38.5. This one right here is 31, 32, 33, 33.5. This one right here is 30, 31, 32, 33, 34, 35, 36, 36.5. And this one right here is 29.0. So we're done with the temperature changes. Now we find out the temperature increase. For this, we're going to require a calculator. 29 minus 21. That's 8.0. Then 36.5 minus 21.5. What you're basically doing is that's 15.0. You're subtracting the final and the initial temperatures to get your temperature rise. 33.5 minus 21.5. You get 12.0. 38.5 minus 22.0, and you're gonna get 16.5. And then 46 minus 22, and you're gonna get 24.0. Okay, so we're gonna see what kind of results are we getting. Volume of sulfuric acid used. In the first experiment, we used 30, then 25, then 20, then 15, and then 10. So our temperature increase is increasing. You can see it for yourself. Our temperature increase is increasing. But over here, there is a decrease. So this might be an anomalous result. I don't know. Just by looking at my readings, I'm expecting. On figure 1, okay, let me just see if I've made a mistake or not, because 20, 21, 21.5, and that's 30, 31, 32, 33, 33.5. So that should be correct technically. I think that, let me check. Yeah, all my readings are correct. Okay, so now I have to complete a suitable scale on the y-axis and plot the results from the experiment 1 to 5, draw a line of best fit. So they've given me the volume of dilute sulfuric acid. They've plotted it for me. I just need to plot the temperature increase. So my highest value is 24 and my lowest value is 8. So I have to start it from 0. So I have to choose a scale. So let me think about it. So it can be 0. This can be 10. This can be 20. and then this can be 25. Is this gonna work? Yeah. And this can be 5.0, 10.0, 20.0. You know, it's important stuff. I'm telling you guys, just add those zeros. They're gonna be like, even though examiner does not say, just add them. I think they're gonna do it. They're gonna make it better, because look what he has done. He has done 0.0. He has done 10.0. So why don't you do this? We also do this. Maybe you guys can get a distinction by doing such stuff. I don't know. And then that's 15.0, and that's 10.0. By the way, you know, I have a distinction. I have a regional distinction in physics. That's one thing about me that I've never shared, but yeah, I have a distinction in physics. O-levels physics. Okay, so now we got to plot a graph. For our first, it's temperature increase is 8 and the volume is 30. So temperature increase is 8 and the volume is 30. Okay, that's 5, that's 6, that's 7, then that's 8. Okay, done with the first point. Then 15 and 25. 15 and 25. Not 25, it's 15 and 20. What am I doing? It's 15 and 25, but in the reverse order. Oh my god. Be careful with such stuff. Okay, so 15 on this scale and 25 on this scale. Something like this. Okay. Then we have 12 and 20. 20 and 10, 11, 12. 10, 11, 12. Okay. And then we have 16.5 and 15. So 15 and 15, 16. Epstein? No, sorry, 16. Sorry. Then 24 and 10. 24 and 10. Okay. 10 and then 20 and then 24. Okay, this seems like a kind of weird graph, like something like zigzag, which should not be like this, but it is. Like, it's not my fault that that's what they're given with. Okay, explain why the temperature increase changes as the volume of dilute sulfuric acid changes. Okay, so we're seeing that the larger the volume we're taking, the temperature increase is decreasing, right? So that's the thing we're observing. This means that the amount of energy that's being released, the amount of heat that's coming out is the same. What's happening is that when we have more acid volume, the heat gets distributed in more amount of liquid. Do you get it? If you have 5 joules of energy and you have 2 volumes of liquid, one is like shallower and one has a lot of water in it. So same energy supplied to this, same energy supplied to this, what's going to get hotter? Obviously the less liquid. Why? Because the amount of energy is the same, but over here the amount of liquid is less, so it's going to get hotter because the amount of energy per unit liquid is going to be more. Do you get it? So that's the thing. If you heat both of them with the same amount of energy, the one that's going to have more liquid in it is going to get less hotter. Okay, so over here we're going to state this thought in words, that the more volume we're using, the less is the temperature increase. More volume of acid causes a lower temperature increase. And the reason for that is because similar amount of thermal energy or heat energy is released. Okay? Acid is in excess. That tells us. Because if acid was not excess, increasing the amount of acid would increase the reaction and would increase the heat. So we're going to write acid is in excess, because despite increasing it, the temperature remains the same. Acid is in excess and same energy released gonna tell that same amount of energy is released. That I think that's enough. Same amount of energy is released every time. If we write heat energy, that's gonna be like a better word, or thermal energy. So we say the same amount of thermal energy released. Okay, extrapolate the line of best fit on your graph in figure 2.1. I just erase. Okay, to reduce the temperature increase if 33 cm cube of dilute sulfuric acid is used. So now I have to extrapolate it, show clearly in figure 2.1 how you worked out your answer. Okay, so first I need to draw a line of best fit, which I didn't draw earlier because I was like a little vague about things. So how do I draw a line of best fit with such results? Just make a line in the center, I guess, something like this. I know it's easier working here, not on paper, but something like this, I think it should be. Because half my results are here, half my results are here. I guess that's gonna be the case. And on 33, let's see what temperature increase do I get. That's 30. Then this over here, this is 31. This here is 32. And this here is 33. Yeah, if we just make it something like this. So how much temperature increase am I getting? I'm getting 0 degrees, right? 31, 32, 33. I mark here to show examiner that I did it from the graph. I mark 33.0 here, and then I tell him that I get a 0 degrees Celsius temperature increase. The investigation is repeated using 2.5 cm lengths of coiled magnesium ribbon instead of 5 cm lengths. On figure 2.1, sketch a line to show the results you'd expect and label the line E. Okay, so now you should remember one thing over here, that your magnesium ribbon is decreasing, magnesium is in excess, okay? Acid is in excess, and we know that if acid is in excess, then magnesium is the limiting reactant, okay? We know this thing, that magnesium got to be the limiting reactant. And if magnesium is the limiting reactant and you decrease the amount of your limiting reactant, your product depends on the amount of your limiting reactant. Again, I'm saying this, the amount of your product depends on the limiting reactant. And if you decrease the limiting reactant, your product is going to decrease, right? So now what we're going to do, we're going to copy this line and make a line that's half of it. That's on like half gradient or something like that thing. No. Don't change this. What do? I just copy it. And then I paste it. That was my previous line of best fit. Now I guess I should make it somewhere like this. And it should look something like this, and I just draw a line below it, yeah? It's for 1 mark. You just have to draw a line below it, because you know that the amount of your heat is gonna like reduce. Why is it the change is gonna decrease? Why? Because the amount of your limiting reactant is less. And you just erase this stuff, the extra stuff. No, not this stuff. From here, something like this. And you make a line like this. I guess it should be like this. And then you label this line E. So that's my line E. Done? this line thing, you just have to do this. Give one reason why a burette rather than a measuring cylinder is used to measure the volume of dilute sulfuric acid. A burette is more accurate than a measuring cylinder. I guess that's the easiest thing that the question you could have asked you. Why do we use a burette instead of a measuring cylinder? Burette is more accurate. Simple. Explain why the contents of the boiling tube are stirred during each experiment. To allow the contents to be evenly distributed, to mix them. I don't think that needs any explanation. Why do you stir things? To mix them. This part is easy. To mix them. To evenly distribute them. To spread them. Use any word that makes sense to you. Describe so that the heat change is even, yeah? Heat evenly distributed. Heat, because we're doing a heat experiment. Heat evenly distributed. So that the heat is evenly distributed. Just write it in good words. Describe one change to the apparatus that will give more accurate results. If we use an insulated boiling tube, over here we're using whenever we do heat experiments. Okay, that's something I'd like to tell you guys, that whenever we do heat experiments, okay, anything related to heat, at the end they're always going to ask you about changes in the apparatus. You always have to write like this: insulate the beaker, or cover it with a lid so that the heat loss is minimum, something like this. So we're going to say use an insulated boiling tube. And the second thing we're going to tell them, why is that? To minimize loss of heat. We don't want the heat to be lost. We need to calculate the heat energy, right, from the thermometer. Let's read further. A student tests two substances, solution A and a solid B. Test on solution A is that you add aqueous iron 3 nitrate. You should know that solution A is aqueous iron 3 nitrate. The tests you should know for iron 3 and for nitrate. Record the expected observation. The student divides solution A into 3 approximately equal portions. So over here what we're doing is that we have FeNO3 thrice. That's going to be the formula of iron 3 nitrate. And then we're taking this solution and putting it into 3 different test tubes, okay? The first portion of A, the student adds aqueous ammonia drop whites. Then in excess, what's going to be the observation for iron 3? What's going to be the observation when you add ammonia? And then you add ammonia in excess. You go to the table below, and then what do? You simply just copy paste the iron stuff. For iron 3, it's going to be red-brown PPT insoluble in excess and red-brown PPT insoluble in excess. For ammonia, you write red-brown PPT insoluble in excess. I don't think this part needs any explanation. You just have to copy paste stuff. Like you're getting 2 marks for just copying it from below. Red-brown PPT, and you write insoluble in excess. To the second portion of A, the student adds aqueous sodium hydroxide. You just copy this and then you write this over here. That's so easy. Okay. To the product from B1, the student adds a small piece of aluminum foil. The student gently warms the mixture and tests any gas produced. So from the product of B1, do you know why they said the product of B1? Because what's the test for nitrate? You add sodium hydroxide and then you add aluminum foil. So from the wording that from the product of B1, they meant sodium hydroxide already added. Because in B1, look, what did you add? In B1, where's B1? This is B1. You added sodium hydroxide. Okay, so that's what they're trying to say. Then you add aluminum foil. The student gently warms the mixture formed and tests any gas produced. Observation. That's ammonia gas that's going to be produced because you have nitrate over here. What's the test for ammonia gas? Turns damp red litmus paper blue. You just copy it from below and write the test. Turns damp red litmus paper blue. Just copy it from below. Identify the gas produced. Ammonia gas. To the third portion, the student adds 1 cm cube of dilute nitric acid followed by drop-wise barium nitrate. Observation, no change because that's the test for sulfate and we don't have any sulfate here. Test on solid B. I guess that's the easiest part. You just have to copy paste this question from below. Table 3.1 shows the test and the student's observations for solid B. Test 1, do a flame test on solid B, light green flame color. Okay, you go below, you check where do we get light green flame color. That means a barium ion is present. Okay, so you just write barium 2 plus here. Okay, add the remaining solid B to dilute hydrochloric acid. Add the remaining solid B to hydrochloric acid. Test any gas produced. Effervescence in a colorless solution turns lime water milky. Obviously, you know there was a carbonate present because this is the test for carbonate, right? And over here, this is a test for barium, light green flame color. Identify the gas produced. Carbon dioxide gas. Identify solid B, barium carbonate. Okay, barium carbonate. Simple. So now we have a experiment question. Let's read it. And then we're going to follow a step-by-step procedure about how to do it. Duralumin is an alloy containing a mixture of metals. The type of metals in it are aluminum, copper, magnesium, and manganese. Okay, no worries. Table 4.1 gives some information about the 4 metals. So first information we're given about aluminum is reaction with dilute HCl. Okay, so that's important stuff now we're being told. Reacts to form a soluble salt. Does not react with nitric acid. Copper does not react with HCl. With nitric acid, reacts very slowly at room temperature and quickly when heated to form a soluble salt. Okay. Magnesium reacts quickly to form a soluble salt and reacts quickly to form a soluble salt. Manganese reacts quickly to form a soluble salt, reacts quickly to form a soluble salt. Okay, we're given with a lot of information. When you're given with tables like these that has a lot of information, you know, you got to extract out what you got to write and you got to like plan properly what to do. Plan an investigation to find the percentage by mass of aluminum in a sample of duralumin. Your plan must include about how you'll calculate the percentage by mass of aluminum in duralumin. You're provided with a powdered sample of the alloy duralumin, dilute hydrochloric acid, dilute nitric acid, and distilled water in common laboratory apparatus. Okay, so now I'm going to just draw a diagram and make you guys realize how are we going to carry out the procedure. So over here, I found a perfect way through which we can measure the percentage mass of aluminum. Over here, the only thing that I think we need is nitric acid. We don't even need hydrochloric acid. Why? Because copper is not going to react with it. But with nitric acid, everything's going to react except for aluminum. We don't want aluminum to react because we want to measure its mass at the end. And everything else is going to react if we heat the solution. So the perfect way is, first you take your duralumin, whatever duralumin thing is. This duralumin thing contains everything, right? Everything, manganese, aluminum, and copper, and whatnot, right? And magnesium and whatever. We weigh its mass, right? After weighing its mass, we take this duralumin thing and then we put it in nitric acid. We put it in nitric acid, everything is going to react except for aluminum. So then we heat it because copper is only going to react if we heat. So we're going to heat the solution. So after heating it, when we're going to heat it, the copper in it is also going to react. And the only thing that's going to be left unreacted is going to be our aluminum. So over here, everything is going to react and form a solution, and aluminum is going to be left unreacted at the bottom, because over here it's written that aluminum does not react with nitric acid while everything else does react. And when we're left with aluminum at the bottom, what we're going to do? We are going to filter the solution out. Aluminum is going to be left on the filter funnel while everything else is going to be collected below as the filtrate. After filtering it out, we're going to wash the aluminum residue, wash it with distilled water, and then we're going to dry it. And after drying it, we're going to measure its mass. Now we have the mass of aluminum and we have the mass of duralumin. Now we're simply going to use the formula. That's as easy as ABC. The formula is simple. What is the formula? Mass of aluminum divided by the mass of the alloy, the duralumin thing, times 100. We're going to use this formula, and now after using it, we're going to have the percentage of aluminum in duralumin. And you just have to write these 5 steps in your own words. Step number 1, step number 2, step number 3, step number 4, step number 5, I'm telling you what are the 5 marks for. And step number 6 is the formula that you're going to use. Done and dusted.